Hi, I'm Adam Breindel. I do a lot of work with Apache Spark, and I teach a lot of classes on Spark with Databricks and NewCircle. And in a lot of classes, there are questions that come up about certain APIs, DataFrames and Datasets, how they work and how to use them. So I wanted to talk a little bit about how those work, when they make sense, and go a little bit deeper technically into the advantages and mechanisms here. Everything we're doing today is on the internet, and you'll be able to play around with Spark 2.0 through Databricks Community Edition. So this is called Modern Spark DataFrame and Dataset, frequent questions, answers, and a look behind the scenes. So what do we mean by modern Spark? Well, about a year ago, we were really excited about the DataFrame API, and until relatively recently, it was marked experimental because of the way the documentation is generated. But really, by this point, DataFrames are the established way to do things in Spark. What I'm going to argue is that not only do they perform better and they're easier to use, but at this point there isn't really any reason not to be using this API. So that's kind of the TLDR. But what we want to do is say, okay, how does this actually work? Not just how do you use it, but when I say it works better, what do I actually mean? So let's go and take a look at some code. What we're going to play with here is a small data set that's actually hosted by MongoDB. It just has zip code data for the United States. So this is not big data, but it makes it really, it's got a little bit of structure to it. It makes it easy to take a look and explore with Databricks Community Edition. So the very first thing I'm going to do here is just retrieve the data set using wget. For big data, it's probably not the best way to do it. You'd probably load data into Spark from HDFS or S3 or something like that. But we're going to retrieve it here since it's a small data set over the web. And we'll just wait for this to download. And it looks like here it is. And I'm going to scroll down. So where did this file go? zips.json. We'll do a pwd here. Looks like we're in /databricks/driver. So how can I get started with this and DataFrames? I'm going to go SQL context read JSON and point it at the file. And I'm going to say register temp table. Which creates a view that I can use to talk about that table in SQL. So I'm going to go ahead and run that. And notice the deprecation warning that came up. That's new because of Spark 2.0. In Spark 2.0, we call this create or replace temp view because register temp table caused a little bit of confusion. So I can use that call, but it generates this deprecation warning. So we'll come down here and try the Spark 2.0 version. Notice also that I use the Spark session object at the beginning of the line. So I say Spark instead of SQL context. In Spark 2.0, because of the proliferation of context objects, Spark context, SQL context, streaming context, there's a new Spark session object that provides an easy entry point for our code. So I'm going to try this spark.read.json and the create or replace temp view. So we'll run this. And we get the same thing, but this shows that we're using the latest API. And then I can hop over here into SQL and just take a look at this table. Not the data, this is the schema of the table. I do a describe on it. And we can see that there's a city, location, population, state. The underscore ID field is actually where the zip code lives. This is sort of a Mongoism. It'll be familiar to you if you've used Mongo, but we're going to go ahead and change that to be called zip. So in this next line, I'm just going to grab the table and say with column renamed, and then I'll create or replace the temp view. So I'm going to throw away the old one and bring a newer one in here. So that's all we had to do to get our data into a situation where we can work with it using SQL. So let's do a very simple analytic query on this thing. What are the most populous cities in Illinois, and how many postcodes do they have? Right? This is a pretty reasonable thing to do with SQL. We've got a select count of zip here, sum of population and city from the zip table we made. Where the state is Illinois, we're going to group by city. We're going to order by the population total descending, and we're going to limit to the top 10. And if we go ahead and run this, just straightforward SQL against this data set, we see Chicago at the top, which isn't too surprising, and a handful of other cities that have 100,000 or 50,000 or more people here in Illinois. Over on the left, you can see the number of zip codes. So we're not going to do a whole lot of analytics work here, but this just is a straightforward query. And what I want to do is talk about, why would we do it this way and not with the RDD API? So there are a couple of reasons. First, I prepared a little example so we can see what it looks like to code this with the RDD API. So to rewind a second, remember this is a simple query. Most populous cities in Illinois, ordered, grouped together, and when we go to do this using the RDD API, first I'm going to run this cell that prepares the file we're going to look at, and this is how we're going to do it. We're going to read the data in. We're going to parse it on the delimiters here. We're going to create these Scala tuples that represent rows. And then to do the query, we're going to filter for Illinois over here. We're going to project out the city and the population. We're going to do a reduce by key. So for each city, we roll up all the population data. Then we're going to sort this thing in a descending order. And we'll do a take 10 so that we can get the results back more efficiently, and we'll print them all out. So I'm going to run this, and I just want you to see that we get the same data. But unless you really kind of enjoy doing things the hard way, this is not easy to read or to write. Right? Once we know what we're doing, if I already explained what the goal is, this kind of makes sense. But it takes a couple minutes to think about how to structure this. You can imagine it's pretty easy to get it wrong. And in 6 months, when I come back to it, or my coworker needs to look at it, it's really not obvious that this is a simple analytics query. So just from a human usability point of view, the SQL is a whole lot nicer. And what I'm going to be showing is that not only is that the case, but the SQL version will run faster, and it will execute a better version of the query than the one that we're trying to do by hand anyway. So now that we've got that comparison down, let's come down here and ask a simple question. Is this the best way to write this query? And I just want to demonstrate something here. So what I wrote is reasonable, but would Spark fix it if we wrote a worse version? So in this next cell, here's a slightly worse version of that same query. It produces the same answer, but why is it worse? Well, I'm doing all of my processing before I filter for Illinois. Right? So I'm doing a lot more work than throwing most of it away. If I filtered first, I'd have less data. This is obvious, and most traditional database systems will do these optimizations for you. But the RDD API isn't going to. And to prove that, let's go and take a look at the job UI and see what just happened. So I'm going to switch over to this tab. This shows my Spark 2.0 cluster that's running. I'm going to click on this link that says Spark UI. I'm going to come over to Jobs, and what I'm going to do first is look at the job I just ran. That's this one over here, job number 7. And what I want to do is take a look down where it says Shuffle Read and Shuffle Write. So in the efficient version of the query, or at least the one that I wrote pretty well, we're moving about 15K, well 14K through this shuffle between the stages. Now, if I flip back and run this less efficient version of the same query, right, we get, nice answer here. But if we come back to the Jobs UI, and if I click on Job 9 and scroll down, notice that we're moving several hundred K through the shuffle. So we're up by, somewhere between 1 and 2 orders of magnitude in terms of the quantity of data that we're making Spark process. And that means that as our job scales up, things are going to take a lot more resources and a lot longer to do the exact same job. So in other words, with the RDD API, the burden is on you as a developer to understand this and to get it right. And if you get it wrong, even if things work, they may work a lot slower. Okay, you can see I just keyed in a little label here that says on to DataFrame and Dataset details. So we'll switch over. First, let's pick up something small. Let's cache this table. We don't really need to cache it, but it's always handy to have it in memory since it doesn't take up much space. So notice that when I run a SQL cache table command, that it actually cached right away. It actually did some work there. This is interesting because typically caching in Spark, when you go through the programmatic APIs, is lazy. Your data doesn't actually get cached until it gets touched by some subsequent action. But when I use SQL and I say cache table zip, it's cached right away. How can we tell? Let's flip over to the storage UI and see if it's there. And here we can see it, in-memory table zip, and we can see that it's actually pretty small. It fits in memory and it's only about 2 megabytes here, so nothing too exciting. but it's all cached in memory from doing that cache table directive. So once we're agreed that we don't want to be using RDDs, which are really kind of an internal API going forward, what about data sets and data frames? Well, what I want to explain here is they're really the same thing. They've always been intended to be the same thing, and now that we have Spark 2.0, they really are. So how can we tell? Well, right here we can do a little check in Scala. Is class of DataFrame the same as the class of Dataset? So if I run this, you can see that it comes back true. And if you want to see where that lives in the code, I'm going to flip over to this tab, and I'm going to scroll down. This is from the SQL package in the Spark code base on GitHub as of today. Right down here on line 45, we define DataFrame to be dataset of row. And that allows backward compatibility. We can talk about DataFrames, but they really are the same thing as dataset. And the reason why that's important is that we want to think about datasets and DataFrames as being very similar. So the differences are much less important than the similarities. We want to program them the same way as much as we can. So datasets offer this strong typing. Instead of just having rows, we can have strongly typed Scala objects in there. But the first thing to realize is this typing is virtual. It's like a view. It's applied when we ask for it, but the underlying data is always stored in a binary language-neutral encoding. We'll demonstrate that later. So when we talk about having a data set and making it be one type or another, we're not actually doing any processing, and we're not actually converting anything. We're just treating it as a certain type when we want to use that in our code. So here's a really quick demo. The traditional SQL context.range call that used to produce a data frame, if I run it now, it produces a data set. Notice that I get a data set of long. The schema has a column called ID, which is a long, just like we used to have with DataFrame. And notice that over here it says ID big int. Right? So that's the actual data type underneath. I can take that data set and I can say, I'd like to treat this as a data set of strings. So if I run this cell, I get a data set of string. And again, on the right, it's still big int. So note the Scala type changes, but the underlying schema stays the same. What is this big int? Well, the underlying types here are language-neutral database style types. So think about the kind of types that you have in a SQL database or in Hive, things like big int and string. Those are the universal underlying types, and they're encoded in a binary format. If we wanted to go back to a data frame, we can call 2df on a data set, and that just gets us rows. So instead of having a data set of the original type, we'll get a data set of row. And you can see that here. So here I've got, when I do a collect, I get an array of row objects that have these numbers in them. So language neutral, what does that mean? Well, I'm not going to demonstrate this, but with an RDD, if I cache it in Scala, and then come in, say, through Python and use the Spark context to find the persistent RDDs, pull back some data, that will actually work, but the data I'm looking at is going to be encoded objects from whatever language created the RDD. So that would mean it's either going to be very difficult to use, or I'll need to somehow decode this myself. I'm sure it's possible, but it's certainly not easy. In this case, we don't have to do any of that. If I take this little list of integers here and I say create or replace temp view numbers, so I'm making a little table called numbers, and now I'm going to come into Python. So here's Python code, and I'm going to look up this table by name, and I'm going to do a print schema on it. So notice that it does show up the same way over here in Python, and I can actually read the contents out in Python. So I'm going to go SQL context.table numbers. I'm going to collect that data back to the driver in Python, and we're going to print it out using regular Python code, and here are my numbers. Right? So Scala, Python, R, SQL, it doesn't matter. The data is all language neutral, and we can access it in whatever way is most convenient for whichever business group needs to do that. So, okay, so how would this work with a more complicated type? So there's, we can have a data set of strings or longs or something, but how does this work with a more complex class? So here's an example. Remember, the class that we're using is purely on the view side, right? It gets mapped nicely against the data, but neither one depends on the other. So recall that we loaded this data from Mongo. It was just some JSON documents, a relatively flat schema. It's got a little bit of nesting where the latitude and longitude are. If I define a case class, so here's a Scala case class called zip. It's got the fields with the same names, zip, city, location, which is an array of doubles, pop, and state. And notice that inside this case class, I've gone ahead and defined some pretend complex business logic. I've specified a latitude and longitude for Chicago, and I've defined a business method called near Chicago, which uses some math to basically find things that are in kind of an ellipsoid near the center of Chicago. So this isn't terribly complicated, but in a lot of business domains, you may have methods that you want to use that are either very complicated, they've been QA'd and built and approved for a long time, you want to reuse those. In some businesses, there's regulatory restrictions. You may have code that needs to be approved by the FAA or the FDA or something like that, and you can't just go and write a similar operation in Spark and put it into production. So if you have code that you need to use as is, or you'd like to use as is, that's one of the places where datasets really shine, because if I have a dataset of zip objects, I can use the methods on zip just like any other method. So let's take a look at an example. First, I'm going to evaluate this cell that defines the zip case class, and then I'm going to take my table called zip, and I'm going to go .as, and then the type zip. And I'll pull back the first record so we can just see what that looks like. And you can see that what we get back is a Scala zip class instance with the data inside. So here's the zip code, here's the name of the city, here's the population, here is the state. What is this mess in the middle? That's actually a stringified version of the array of double precision floats. We can look at that if we want in this next cell. So I'm going to do the same thing. I'm going to pull out the first record, and I'm just going to pull out the .loc member. And here you can see it's an array of double, and there are the actual coordinates in there. So, okay, so how can we use this data set object to do some analytics? Well, remember I said that data sets are really the same as data frames, so don't think of them as being object collections like an RDD. Think of them as being just another way of dealing with a table, although maybe it will accommodate more complex tables or documents. So here I'm taking the data set, I'm saying group by state, count, and then order by state. So I'm just looking to see which states have how many records for different zip codes in there. And I'm calling .show. So what we can see is that Alaska has 195, Alabama has 567, and so on. Might be more interesting if we ordered by count. We could see which states have the most zip codes or the fewest. But this is showing how we can use a data set. So we're going to use this just like a data frame. Now, if I do want to use my complex business logic, and I put complex in quotes here, but you may have more sophisticated code in your company you need to use, here I'm going to read in that same file, and I'm going to say .filter, and I can filter on a column expression just like I can with a data frame, but with data set I can also filter on a function, a lambda, and I can just use the method that's defined in this zip object. So here is my data set filtered for zip codes near Chicago. And here's kind of just the first 20 that come up in the list. So using existing domain logic that you may have invested years in building is as simple as plugging them right into certain APIs in the data set, just like this highlighted section right here. So we just looked at how we can use data sets together with some custom business logic. And I want to talk for a second about the query optimization. If you want to know a lot of details about the query optimization pipeline in Spark, which is called Catalyst, there are some fantastic talks by some of the folks who have built it, including Michael Armbrust, from Spark Summit. So, and in our 3-day Spark classes, we actually go into detail about how this optimization pipeline works. What I'm going to do today, though, is just give you a quick demo if you wanted to actually see with your own hands and eyes how this thing, that it actually does optimization. I've got a query or two that we can take a look at. So down here, we're going to take the same data set. We're going to find population greater than 10,000. We're going to lowercase the city, just as an example of some operation you might be doing. in your logic. So this lowercase is a built-in function. You might be using some other function here. We're going to project that out. And then we're going to filter for state equals Rhode Island. So recall that when we did the RDD version, we said that pretty much what you write is what Spark is going to execute. So the pipelined operations ran in the same order that we coded them in, and that turned out to be a bad order in one of the queries and a good order in the other, and we could see that Spark ran what I wrote. Here, we want to see whether Spark will do something a little bit different. So if I do a collect here, we can see that the bigger cities in Rhode Island, we've got maybe 20 or 30 of these. This is what the data looks like. Let's go and see how Spark is going to execute this. And we can do that by calling explain. So this is kind of like asking for a plan on a SQL database. We can say explain true, and that'll get us the detailed execution plan. So I'm going to scroll down here and we'll take a look. See if I can expand this so that we can see the whole thing. So here are the 4 stages of plan. We've got the parsed logical plan. That's pretty much what I typed in. It's just Spark saying, okay, I understand what you keyed in here. Then we have analyzed logical plan. That's the parsed logical plan combined with catalog information, so combined with the names of the data sets and the types and the columns. Then we have optimized logical plan. So notice the difference between the analyzed logical plan and the optimized logical plan. So in the analyzed logical plan, we start out with this project, and we alias it, and then we're filtering on the population, and then we're projecting the city and the lowercase version of the city, and then we're filtering on the state, and then we're pulling out the lowercase version of the city, because that's the only field that we asked for at the end. So we have a lot of operators here, and they're just in the order that I keyed them in. They're not in the optimal order. Down here, under Optimized Logical Plan, notice that Spark has applied a number of rules to simplify this query. So first thing that we're doing is we've got a filter operation here, and we've moved the filter before any of the projections. And we've also combined the 2 filters. So take a look. In here we have state Rhode Island and population greater than 10,000. So we've moved the filters earlier in the query, and we've combined them together. And then after that, all we have to do is pull out the lowercase version of the city. So you can see here that it's easy to ask Spark what the plan is actually going to run like. And you can see the difference between the query that you punched in and the final one that Spark has optimized. And so unlike with RDDs, I don't have to write the perfect query every time. And in fact, a lot of different queries I can write in whatever order is most natural or most readable for my team, and it'll end up being produced in an optimal way by the Spark Catalyst engine. So notice these stars over here in the physical plan. So these are connected to a brand new feature in Spark 2.0 called whole stage code gen. So you'll be hearing a lot about whole stage code gen over the next few weeks. And the idea is to take all of the pipelined operations between shuffles, and that's what makes up a stage in Spark, and actually, instead of composing those operators and running data through using an iterator, which is like a cursor type approach, instead to generate a block of code that represents that computation as if that was the entire thing that you were trying to do, and then compile that code and execute that code against the source data. So to take a look at whole stage code gen, first thing I'm going to do is take our query where we converted the data set to zip codes and filtered for near Chicago, and I'm going to ask Spark to do an explain on that. And if we scroll down and take a look at this plan, so down here near the bottom, we can see that whole stage code gen is turned on, and the function that we wrote, our near Chicago function, that shows up right here, where it says filter function1.apply. So our custom code has actually been integrated right into the pipeline of code that's going to get whole stage generated and then compiled. And this helps a lot because it means that Spark isn't doing one set of work from compiled code, then separating out our work to process near Chicago, and then going back to some other optimized code. It's all going to be inline. And if you want to take a peek behind the curtain and really see what this code looks like, you can do that by importing this particular code right here. So if we bring in org Apache Spark SQL execution.debug, and then we take the exact same query, and at the end where we had explained, we say debug Codegen. If we run this cell here, this shows the actual code that's been generated for this query. So it's Java code, and it's machine generated, so I don't expect this to make a lot of sense the first time you see it. You know, like all machine generated code, it has two interesting properties. One is it's very consistent, and two is it can be pretty hard to read for a human the first time you look at it. But if you are interested and you spend a little bit of time with this code, you can actually see how our function application is integrated directly into the rest of the code that represents this query. If we come all the way down to line 83, we can see that that's where we're getting our filter. So filter value 1.apply. And if we scroll back up, we can see what that is. Here we can see on line 55 that filter value 1 is a Scala function, and it's a cast applied to this filter object that we fed in. So our code that was originally our business domain code about interesting customers or conditions near Chicago is actually getting compiled directly into the code that Spark is executing for this stage. So that's all that we're going to talk about as far as whole stage code gen. There'll be a lot of other materials online from Spark Summit that talk about whole stage code gen in terms of performance and other details, but I wanted to give you a little flavor of how you can see that that is actually happening and how you can even take a look at the code that Spark is emitting. A couple more things that we want to make sure that we talk about why you would want to be using DataFrame and Dataset. So you get Hive integration for free. A lot of companies have a big investment in Hive and related tools, and Spark will automatically work with your Hive metastore. So your Hive tables are available in Spark, and you can take data in Spark and make them available as Hive tables really easily. So just to give a quick example, we can take our zip table right here and say .write .save as table Hive_zip, and that succeeds. And then the question is, well, where did it go, and how do I know that it's available to Hive? Well, if I look under the Tables tab here in Databricks, I can see the Hive zip table. That's showing me the Hive metastore. But what if you're not on Databricks or you don't believe me? Let's take a look a little bit further down. Here's the access to the zip table using the Spark session that we mentioned earlier. So in Spark 2.0, we can say spark.table. So given that Spark session, we can ask for the catalog and the databases that Spark knows about, and we can see where the Hive data actually lives. So I'm going to do a spark.catalog.list databases, and you can see we get back a data set that says, okay, here's the default Hive database, and here is the Hive warehouse. So the default warehouse location in Databricks, in this version of Databricks, is under user Hive warehouse. In your installation of Spark, you just configure this to match wherever your Hive installation is. And if we want to see that our data actually lives under there, we can do an ls and look under user Hive warehouse Hive_zip, which is the name I gave to that table that we just wrote out. And here you can see there's Parquet data underneath that folder. So the data actually has been moved into the Hive warehouse. So that almost concludes our tour of DataFrame and Dataset. So kind of wrapping up and looking to the future, all of the new development, or nearly all the new development in terms of new APIs and optimizations on Spark are focused on DataFrame and Dataset. So you get the benefit of all of that research and implementation when you're using these APIs. If you're doing machine learning, there's Spark ML or the ML Pipelines API that you've probably heard quite a lot about over the past year. Here's a link to the docs. More recently, DataFrames. So there used to be an API called GraphX. There still is. That's the traditional API for graph processing over RDDs. Well, if we want the performance and storage advantages of DataFrames and Dataset, what we're going to do is use DataFrames, which is an implementation of graph algorithms over DataFrames. Here is a link to a really cool demo that features analysis of passing among the Golden State Warriors, where they use something like Google PageRank algorithm to look at who are the key players on the Warriors. And you can probably guess who's getting the ball the most. And the last thing I want to show, so we've said we're going to use DataFrames as the underlying infrastructure for moving around our data. We're going to do Spark ML to do machine learning on top of that. We're going to use DataFrames to do graph analysis on top of DataFrames. And the newest thing is structured streaming. So you may have seen some talks about building streaming directly on top of DataFrames. And the early iteration of that is out in Spark 2.0. And I put together a really quick demo of just kind of a hello world of structured streaming so that you can actually see what this looks like. So instead of using the traditional streaming API that's focused around RDDs and D streams, what we're going to do is we're going to create something called a continuous query that reads data from some streaming source, does some processing on it, and that data is going to flow out somewhere else, and we can do whatever queries we'd like on the live stream. So let's just take a look at a fun demo that we can use to start with. What I'm going to do here is prepare some folders. I'm going to use file sources and sinks for this demonstration. So I've got a folder stream in where I'm going to put some data into my stream. These might be transactions or something like that coming in. Then I've got stream out. This is where I'm going to write my data to. And in order to support fault recovery, we're going to set up checkpointing under a folder called stream/ck. I'm also going to define a schema so that Spark knows the shape of the data before the records actually start coming in, and each one's going to have a last name, which is a string, an email, which is a string, and a number of hits, like in a web analytics scenario, for example, number of hits, which is an integer. So I'll go ahead and run this. Okay, so now we get down to the fun part. Let's start our stream up. First, we're going to set up the source, spark.read.formatjson.schema, and we pass the schema we created, and we're going to say .stream, and I'm going to point at this input stream. So this particular path is dbfs, that's data that actually lives on S3, that's attached here through Databricks. So I'm going to run that. And notice that I get back a DataFrame object. And now I'm going to define the processing we're going to do on this stream and where we're going to write it to. So the modified version of this data is defined right here. I'm going to take the data that comes through. I'm going to pull out the last name. I'm going to lowercase the email. It's kind of a normalization maybe, and assign that to have the name email. I'm going to get the current timestamp. So the time that we're processing the event, I'm going to call that now. And I'm going to grab the hits, the number of hits that came in. Then I'm going to take this modified data, and I'm going to say write, and I pass the checkpoint location, and then I say .startStream, and I point to the output folder. So let's go ahead and run that. And you can see right here in Databricks, we can visually see that something is running. It says stream query 0, status active. If I open this disclosure triangle here, it says awaiting data. So we'll see if we can feed some data in here, and we'll see what happens. So in this next cell, I'm using echo in a shell command to actually take two JSON records and drop them into a file in the temp directory. So we'll do that. That's the temp directory, not the actual streaming directory. And then I'm going to move this file into the streaming input directory. Think about this as being like when you do log rotation, right? You've finished creating a file that contains some records or events, and then you rotate over to a new file name, or maybe move the existing log file into another location. So I'm going to toss this file right into the stream. And we should see some data showing up. In fact, you can see right here, it just changed the UI under stream says source is 1. It shows some details about the source and the last offset, and it shows the sync. And we can actually query the output, which is a Parquet file here. So here are the records that came through. So far we just have one set of records. So what happens if we wanted to do some analysis on here or send in some more data? So if I wanted to, say, roll up the total number of hits by email, so far we just have 3 for Jones and 5 for Smith. So what happens when this next event happens where Smith sends in another 12 hits? So we'll do the same thing. We echo to a file. We're going to rotate that file here into dbfs stream in. And now we're going to run the query, the same one we did before. And you can see that Smith has 17 hits, right? So we've gotten another record. We did the same query we did before, and now we're seeing live updating data. If we scroll back up, we can see that the offset has moved in the stream, so now it says last offset number 1. And if I want to shut the stream down, I'm going to come down here and go stream.stop. So this is just a very simple hello world of structured streaming, but this is the new streaming API that you can use directly with DataFrames. It's shipping in Spark 2.0 right now. Probably the easiest way to try out Spark 2.0 is through Databricks Community Edition, so you can sign up for a free account and run this exact code that we've been playing with. We'll go publish this online so you can import the same notebook and try it. Or you can download the open source Spark project code and build it yourself from spark.apache.org. Hopefully this helps clarify why DataFrame and Dataset are the future of programming with Apache Spark. You get a little look under the covers here. If you want to learn more, there's great material online from Spark Summit. And if you want to learn to do Spark programming yourself, NewCircle has public classes, and for teams of 5 or more, we can come on site and do an in-depth Spark programming class. Thanks for watching.